Hey everybody, this is Larry. This is day 9 of the Leetcode Daily Challenge for July. Hit the like button, hit the subscribe button. I'm going to do the explanation now. You can watch me do the live coding later. Join the Discord as well if you want to have any more questions. And let's get started on today's problem, maximum width of binary tree. So the thing about this problem is just kind of, so I would just first read the problem, but to be honest, the problem statement wasn't super clear, or at least there are a lot of ways to say certain things that make it quote unquote common, but you have to make sure that what you think is the problem is the problem. Otherwise, it's going to be a bad time for everybody. But the thing to notice for this problem is that going from what you want to do is have an invariant that that the leftmost number for a given level is the distance between them. There's a way to calculate it easily, and there are a couple of ways to think about it, I think, and you could probably have done some pre-order type thing to do some counting, but the way that I thought about and the way that kind of this problem reminded me of was a very standard full table or full tree measuring thing, which is just using the formula that if you may come across this, which is that given a full array, if you're given a node, the left node, doing some ASCII art, and let's say this one is just index for some index, the left node would be 2 times I or index, and then the right node would be 2 times I plus 2. So sorry, this is plus 1. And this depends on whether you want to start at 0 or start at 1. It's roughly, it doesn't really make that much of a difference. But yeah, and the nice thing about this invariant is that, there are additional nice things about it that it doesn't really that doesn't apply here. But the big thing is that as you kind of grow this out more and more level, then this becomes 4i plus 2, 4i plus 3, and then 4i plus 4, 4i plus 5, right? So the key thing to note is that from the left to the right, whether that space is full or not, or filled or not, it increments by 1 every time. So all you have to do then is that for every level, it's easier to calculate what the rightmost is by just taking the max, and to take the leftmost by taking the min, and then the delta of those two numbers will give you the width of at that level. And then after that, you just have to take the max of all the widths. So that's kind of how I thought about this problem, and that's how I coded it up by having a min hash and I guess I could have used an array and expanded as I needed it actually. But the point here is that I just keep track of the min per level and a max per level, and I just keep track of that. If I go left, I do index times 2 plus 1. If I go right, I do index times 2 plus 2. And then for every time we run it across, we look at, is the current max and the min of a current level bigger than our current best? If it is, then we just update it. And then at the very end, we just set up a very straightforward recursion for the depth first search to look at every node. This is going to be O of n time, because you have to look at each node at least once. It's going to be O of h space, because you store a couple of values per level, and this the stack space and stuff like that could be O of h, which could be worst case O of n, but O of h to be more precise. And that's all I have for this problem in terms of the explanation. I hope that this was okay, because I think this is a little bit fundamental. So if you definitely don't know how, if you want to get the proofs on this, this comes up a bit on binary trees and binary full trees. So definitely do some studying on that. But let me know what you think. Hit the like button, hit the subscribe button. I would say you know, and I say this all the time about depth first search problem or recursion problems or tree problems even, all three of those things, which is that it's mostly fair game for interviews and competitive programming. So definitely make sure you practice it, make sure you understand it, and this kind of technique comes up randomly and all over the place. So definitely be a little bit familiar with it. Not any technique per se, but just the depth of search, but also labeling things from I to 2i plus 1 and 2i plus 2 as a full tree. Yeah, that's all I have for today. Let me know what you think, and hit the like button, hit the subscribe button, and yeah, join the other Larry for the live coding portion right about now. Hey everybody, this is Larry. This is the 9th day of the July daily challenge. Let's take a look at the live coding portion of the thing. Let's go. Maximum width of binary tree. Given a binary tree, write a function to get the width, the maximum width of the given tree. The width of the tree is the maximum width among all the levels. The binary tree has the same structure as the full binary tree, but some nodes are null. The width of one level is defined as the length between the end nodes. The leftmost and the rightmost non-node at the level where the no nodes between the end nodes are also counted in the length calculation. Okay, so this is 4. This is 5 and 3. Okay, maybe. So this is 1, 2, 3, 4. Fourth level 8. What? Okay. So I think with these kind of problems, it's just about, well, for me, what I was trying to do is figure out what, just definition-wise, for clarification. That's what I look for the examples for, and trying to make sure that I really understand it. And also partially to find the invariant of a problem, which is something that, you know, doesn't change as you change other things. And here is the one that's 8. So the question is, well, how do you label these in a way such that you know, you get the max per level? And I think it's not that bad. So I think you can actually I was playing around with different ideas, but I think the thing that I'm going to do is just use the kind of textbook encoding of the binary node, meaning given the root node, go left is 2 times I, and then go right is 2 times I plus 1, or maybe I'm off by 1, but something like that. And then I just keep track of all of them by using a depth first search, and then just get the min and the max of every level, and then loop over that. So yeah, let's try that. Okay, so I'm gonna do it with depth first search. With a node, and let's just call it yeah, let's just call it index for the node index or something. Oh, and maybe just a level, just for us to keep track a little bit easier. I'm gonna keep track of things in a hash table so that it's slightly easier. You could use your own thing for however you like, by having a what I call a min hash, just a hash table that contains the minimum element, and then the max hash, which is the same but for the max. So then now let's go, if node is none, then we just return. Otherwise, min does the value do anything? The value doesn't do anything. We're just there to illustrate, maybe. Okay, so min hash. Okay, so if level is in min hash, then we just take the min hash of that level is equal to hash index. Else, otherwise we just set min hash level is equal to index. Oops, this is not even right. Oops. Min of min hash of level index, and then the same thing for the max. if level in max hash. Though technically these two things are definitely correlated, so we could have done something about it, but it's fine. And then now we do what we said about the left and the right, and I think that should be okay. We would have to start, so it's okay. So DFS node.left, level +1, index times 2 +1 for the left, and then do the same but index times 2 +2 for the right, and then that's it. Pretty much we have to loop through it to get it. And the reason why this works is that the invariant is that on the same level, the leftmost will, this you could prove to yourself with some maths that the next level, well, first of all, there's no overlaps in the numbers, but also that going from left to right, everything is going to be off by 1, and the proof, it'll be either in the before and the explanation part, so you may have already heard it, or this is a pretty standard textbook-y way of doing it, so you may just be familiar with it. But yeah, so now we just kick it off with this. Yeah, kick it off, and then I was thinking of maybe just looping through it once more time, but through the keys per level. But we could also just actually have a global. I think either way is fine. It doesn't really matter that much. Do we want the min or max? So we want the max, so let's just set the best is equal to 0, and then here best is equal to max of the best, or max of hash of level minus min of hash of level. Yeah, and then we just return best. Ooh, did I not? Oh yeah, have to set non-local the best, so we can actually use it. This is kind of annoying. They don't actually give you the input. Also, I'm off by 1, but that's fine. This is just because we have to make sure that they're inclusive of both ends, and this was not. Yeah, I was going to think about putting in more test cases, and I will just do the case of like 1 node and 2 nodes and 3 nodes, but I feel like it's just too much typing otherwise. I wish there was something to copy and paste for these cases, but it looks okay, so let's submit it and give it a go. Cool. Yeah, so what is the complexity? Well, we look at each node at least and at most 1, so exactly once, so with a depth first search, so it's going to be O of n, which is linear. The space, well, it's going to be height, or O of h for the height of the tree, because we keep a reference for each of the level. You could probably have done this with O of 1. Well, I guess it'll be, if you put things on the stack, it'll still be yeah, so it'll be O of h either way, I suppose. I was going to say that maybe you could put some, if you do post order or something like that, and then you could do some maths that way. But that would still, have you would still have O of h stack space to keep track of stuff. So yeah, so O of h for space. Yeah, and I always say that for search problems are pretty fair game for both interviews and competitive. So definitely practice it. Hope you had a good time, and hope that this was good enough for you. And let me know what you think. Hit the like button, hit the subscribe button, and I will see y'all tomorrow. Bye bye.